Hello, my name is Max Mowbray. Thank you for coming to see our poster on the derivation of an optimal control policy from process data and reinforcement learning. My supervisors are Professor Robin Smith, Dr. Antonio de Rio-Chinona, and Dr. Dongda Zhang. The focus of this work is in the application of model-free reinforcement learning to process systems engineering. There are many directions to research within the application of RL to process systems engineering. However, one approach is to find means with which we can reduce the technical and computational intensity of RL-based methods. As such, the conceptual contribution of this work is the development of a two-step offline-online learning control framework where we essentially leverage existing industrial datasets to reduce the technical and computational demands of RL-based policy learning. So to explore this work further, we'll first provide a quick introduction to reinforcement learning. So reinforcement learning essentially is a field constituted by a set of different learning algorithms that all aim to learn an optimal control policy based on formulation of a control problem as a Markov decision process. So an optimal policy within the Markov decision process essentially maximizes the value of process evolution and expectation from some distribution of initial states across a discrete time horizon. RL is one such approach to learning an optimal policy in an MTP, and RL is typically most powerful when it's combined with deep learning. And essentially, RL, in this combination of the two, provides a framework for learning optimal control, where deep learning enables us to learn complex representations of the system state, such that we can generalize decision making across the continuous state and action spaces or state and control spaces that are characteristic to the process industries. And essentially, this mitigates the problems or the curse of dimensionality that is often found with dynamic programming approaches. However, the combination of deep learning essentially demands a lot of data and a lot of compute to learn reinforcement learning policies. And furthermore, typically a degree of policy tuning or algorithm tuning is required in order to get the control behavior that one desires in the case of reinforcement learning. So this combination essentially means that RL policy learning is both compute and expertise expensive. So if we were to ever see the development or the rollout of RL-based policies within the process industries, especially for perhaps continuous processing, then we will need to research means to reduce this intensity in policy learning. So the main contribution of this work arises perhaps in the offline learning section of the framework, where we essentially introduce a concept known as apprenticeship learning. The field of apprenticeship learning is constituted by a set of different methods that aim to recover a control policy from the process data which it generates. In order to do this, we need to first be able to quantify or characterize the process data that we're presented with from the existing control policy or existing control scheme. The general approach in which we aim to do this is by the definition of a set of or bag of different control hypotheses, where each control hypothesis is represented by a distinct basis function. Each of these basis functions is then hand designed based on knowledge of the control task at hand, but essentially we're then able to quantify process data that's generated on performing control for a given control task by the sum of the fulfillment of these control tasks across discrete time horizon, or the length of the rollout of process data. In essence, apprenticeship learning provides solution to the problem of extracting control policy from process data by constructing the reward function of an MDP as typically a linear combination of these basis functions or these control hypotheses. And then the problem is reduced to learning the optimal weighted combination of these control hypotheses in the form of a weight vector. And we know when we've learned the optimal weight vector because we are able to essentially match the trajectory characteristics of the learned policy that's learned through RL in solving the MDP to the trajectory characteristics of our process data, which is generated by an existing control policy. So in the process industries, we have a lot of data that's generated by existing control schemes that we can use to essentially hot start the reinforcement learning process by extracting parameterizations of those control schemes into perhaps a neural network form. And this is essentially the idea that we're presenting in the offline section of our methodology. The idea is then that once we have this parameterization of existing control schemes, we can then transfer the RL-based parameterization to the online setting where we are able to continually learn under the objective of the real process to improve the policy further. Here we demonstrate this concept on a case study which consists of a multiple input, multiple output control problem with the presence of process disturbance and measurement noise. And essentially we try to learn an existing PID control scheme in the offline framework, and we show through the definition of a key performance indicator that we're pretty well able to extract the PID control scheme or the behavior of the PID control scheme through at most an error of about 10%. We then show that through online learning, we're able to reduce the overshoot that is present in the existing control scheme and improve the policy further. We hypothesize that this may aid in the realization of reinforcement learning-based control schemes, which update themselves automatically and will ultimately reduce downtime in maintenance and recalibration. For more information about this work and for greater information on the case studies which we have presented in this work, please see our paper and poster presentation. Thank you.